Okay, students, let's get started with the past papers of O levels and IGCSE physics. The topic for today is current electricity. Okay, so let's look at the first question. Figure 9.1 is the current voltage graph for a filament lamp. Okay, so this is the current voltage graph for a filament lamp. Okay. Figure 9.2 shows an incomplete circuit diagram of the circuit that a student uses to obtain the readings for the graph. Okay. So this is an incomplete circuit diagram through which you will obtain current and voltage readings. This graph is for a filament lamp. So one thing that we need to show in this circuit is a filament lamp. And how will you measure the voltage across a filament lamp? Always remember to measure voltages, you apply a voltmeter in parallel. Simple. Secondly, can you see there are multiple current and voltage readings in this graph? How will you get multiple current and voltage readings from the graph? By varying the resistance of the circuit. How can you vary the resistance of the circuit? By placing a variable resistor. This will help you in varying the resistance of the circuit and getting multiple values of the voltmeter and the ammeter. This is a 3 marks question. If you draw all three symbols, voltmeter, lamp, and a variable resistor, you will get a 3 on 3. Let's further move ahead. The ammeter used by the student has these ranges. The ammeter used by the student has ranges 0 to 10 ampere, 0 to 1 ampere, 0 to 100 milliampere, and 0 to 10 milliampere. Explain how the student uses different ranges. Okay, how will the student use different ranges to obtain readings which allow all 9 points to be plotted precisely on the graph while using the ammeter safely? Okay, so which ammeter should we use for these readings? If you can see, for the first half, that is from 0 till 1 ampere, that is still 0 to 1 ampere till here. You can use this ammeter, 0 till 1 ampere wala. For the first half, that is 0 till 1 ampere, you can use this ammeter, 0 till 1 ampere. And for readings greater than 1 ampere, you can use the 0 to 10 ampere wala ammeter. So you can write it here readings, for readings less than 1 ampere, less than 1 ampere, use ammeter, ammeter, use ammeter with the range of what? Use ammeter with the range of 0 to 1 ampere. Secondly, for readings greater than, for readings greater than 1 ampere, use what? Use ammeter with what? Use ammeter with the range of 0 till 10 ampere. Simple as that. State how figure 9.1 shows that the lamp does not obey Ohm's law. Any object that does not obey Ohm's law will have a graph that is a curve. Will have a current versus voltage graph that is a curve. So you can write the current versus voltage graph is a curve. Simple. This shows that the uh, lamp is not obeying Ohm's law. Use figure 9.1 to determine the resistance of the lamp when the voltmeter reading is 0.4. Okay. So if the voltmeter reading is 0.4, let's come here. Let's zoom in a bit. And let's erase this highlighting so that we get the accurate reading as possible. A 0 0.4 volts will be somewhere here. This is your 0 0.4 volts. Let's extrapolate this line so you have this thing as your current. That is what? This is 0.5 ampere. When you have a voltage of 0.4, your current is 0.5 ampere. Let's plug in these values and calculate the resistance. The voltage is 0.4 volts. The current is 0.5 amperes. Can you calculate the resistance? Yeah, you can surely do that. You will say voltage over I is equals to your resistance. Your voltage is what? 0.4 divided by zero point 0.5. This gives you a value of 0.8. 0.8 ohms is your resistance. Okay. You have to calculate the resistance when the voltmeter reading is 6 volts. Okay, let's do the same procedure. At 6 volts, you have a current of what? See, 6 volt is the extreme point. At that extreme point, your current is 1.8. So let's plug in these values as well. Let's plug in these values as well. Voltage is 6 volts, current is 1.8 ampere. Can you calculate the resistance? Yes, resistance is equals to voltage over current. Voltage is 6, current is 1.8. Divide both of them. This comes out to be 3.3 ohms as your resistance. 3.3 ohms as your resistance. Let's further move ahead. Explain why the resistance of the lamp changes as voltage changes. So you can say as voltage increases, this causes the temperature to increase. This causes the temperature to increase or change, you can say, to change. However, we should write it with the word of change because the examiner has asked us what will happen if the voltage changes, not when the voltage increases. As the voltage changes, this causes the temperature to change, and hence the molecular vibrations change. Molecular vibrations change. This causes the resistance. This causes the resistance of the lamp to change. Simple. Let me read out this answer loud so that I am sure that I have made no mistake in writing it. As voltage changes, this causes the temperature to change and hence the molecular vibrations change. This causes the resistance of the lamp to change. Simple. State how the resistance of a wire depends on its length and how does it depend on its cross sectional area. So resistance of a wire is directly proportional to length and resistance of a wire is inversely proportional to its area. Simple. Okay, let's read out this question. The student obtains a long sample of the same wire of wire as the filament in the lamp. Okay, so now you have a long sample of wire that is similar to the wire in the filament lamp. The wire he obtains has the same cross sectional area. Okay, so the area is same. Area is same. And he cuts a 1 meter length of the wire and measure its resistance at room temperature. Okay. He cuts a 1 meter length of the wire and measure its resistance at room temperature. Okay. So if you are at the room temperature, that means you will have a low temperature comparatively. A low temperature refers that you will have a low voltage across the filament lamp or the wire. Low voltage across the filament lamp or the wire. Okay. He obtains 16 ohm as its reading. Use the appropriate resistance value from D. Estimate the length of the filament wire in the lamp. Okay. So we have to tell what is the length of the filament wire in the lamp. Okay. First of all, in part D, you have two voltage values 0.4 volts and 6 volts. Which one is more reasonable to take? This one. 0.4 volts and a resistance of 0.8 ohm is much more reasonable to take because room temperatures are low temperatures and at low temperatures your voltage will be less. Okay. Now, if at room temperature a length of 1 meter of wire has a resistance of 16 ohms and your filament lamp has a resistance of 0.8 ohms, what will be the length of your filament lamp? Just apply ratio method. Put a x here. 0.8 divided by 16 gives you your value of length or x. 0.8 divided by 16, this gives you a value of 0.05 meters. And why was I able to apply ratio method here? Any geniuses in the chat who would like to answer this? Why was I able to apply ratio method here? Because I know resistance is directly proportional to length. Any two quantities that are directly proportional, in that we can apply ratio method. Let's further move ahead to the next question. A circuit contains a battery of electromotive force 4.5 volts and a 28 ohm resistor and a variable resistor. Figure 6.1 is the circuit diagram. Okay. The battery consists of three identical cells in series. Determine the EMF of each cell. So if you have 4.5 volts and there are three cells, what will be the EMF value of each cell? Very, very easy. Let's write it down. Oh, let's write it down. 4.5 divided by 3, 1.5 volts is the EMF of each cell. The potential difference across the variable resistor is 2.5 volts. Okay. So 2.5 volts is being received by this variable resistor. Okay. Let's further move ahead. State what is meant by potential difference. Very, very easy. Work done per unit charge, per unit charge in moving a charge, in moving a charge across an electrical component, cross an electrical component. Simple. What are some examples of electrical component? Thermistor, resistor, variable resistor, LDR, LEDs, all of them. Calculate the resistance of the variable resistor. We have to calculate the resistance of the variable resistor. Okay. So first of all, if this thing, variable resistor, is receiving 2.5 volts, what will this 28 ohm resistor be receiving? This 28 ohm resistor will be receiving 4.5 minus 2.5 is equals to 2 volts. So the 28 ohm resistor is receiving 2 volts. It has a resistance of 28. Can I calculate the current in the entire circuit? Can I calculate the current in the entire circuit? Yes, I can do that. V is equals to IR. The voltage received by this resistor is 2 volts. The current, I don't know. The resistance is 28. Current comes out to be 1 over 14 ampere. Obviously, you can convert it into decimal points as well. Okay. Now, this current is also flowing in this variable resistor. The variable resistor now has a current of 1 over 14 ampere. Your voltage value is 2.5. Can you calculate the resistance of the variable resistor? Yes. You can partition it here and you can say resistance of variable resistor is what? Resistance of variable resistor comes out to be what? V is equals to IR. What is your current? 1 over 14. What is your okay, you don't know the resistance, so you have to calculate the resistance. The voltage across this is 2.5. The current is 1 over 14. Can you calculate the resistance? Yeah, you can surely do that. 2.5 into 14. This comes out to be 35 ohms as your resistance of the variable resistor. Pretty simple. If you just apply V is equals to IR 2 times. Let's further move ahead. A boiler, this is a new question. A boiler containing water is plugged into a 320 volts main supply. The heater in the boiler is operating at full power. The power by the heater is this. Okay. Calculate the current in the heater. Very easy. Power is equals to IV. Your power is 2.8 kilowatts. 10 into 10 is the power of 3 is equals to current into the voltage, that is 230. Can you calculate the current? Yes, 2.8 into 10 is the power of 3 divided by 230. This comes out to be what? 2.8 into 10 is the power of 3 divided by 230. This gives you a value of what? 12.2 ampere. Simple. The wiring in the cable from the socket and in the boiler remains safe and does not overheat provided that the current is less than 20 ampere. Okay. So the wiring does not get overheated provided that your current is less than 20 ampere. Suggest a suitable rating for the circuit, fuse rating for the circuit. So obviously the fuse rating will be less than 20 ampere because the wires start to overheat at 20 ampere. Secondly, the fuse rating should be greater than 12 ampere because 12 ampere is the working current of the heater. So let's take a middle value, let's say 15 ampere fuse. Let's further move ahead. The specific heat capacity of water is this. You are given C. The heater is used to increase the temperature of 6.3 kg of water. This is your mass. In a certain time, the temperature of the water increases from this to this. This is your initial temperature. This is your final temperature. Calculate the change in internal energy of the water. What will you do? Q is equals to mc delta T. What is M? 6.3. What is C? 4200. What is delta T? 49 minus 23. This comes out to be what? 6.3 into 4200 into 49 minus 23. This comes out to be what? This comes out to be 6.8. 6.9 I would say into 10 raised to the power of 5 joules. Let's further move ahead. The heater supplies thermal energy to the water at a constant rate. It takes more time for the temperature of the water to increase from 49 degrees centigrade to 75 degrees centigrade than from 23 to 49 degrees centigrade. So the examiner is trying to say that if you heat the liquid from 49 to 75 degrees centigrade, it requires more time compared to heating the liquid from 23 to 49 degree centigrade. Both of them have the same temperature change of 26 degrees centigrade. But this one is taking a larger time. Why is this the case? Why it takes more time for the temperature to increase from 49 to 75 degrees centigrade? Why? Because more heat is lost to the surrounding. Because more heat losses at higher temperatures. More heat losses at higher temperatures. Simple. Let's further move ahead. Let's see the next part of this question. Figure 10.1 shows the heater at the bottom of the water in the boiler. Okay, so this is your heater. This is your heater. Explain how thermal energy from the heater transfers throughout the water. Okay, so the air surrounding the heater becomes hot and its volume increases. Hence, it rises to the top. Consequently, cooler, denser air falls to the ground like this. So you can write your answer like this. The air, the air surrounding the heater, surrounding the heater expands, surrounding the heater, surrounding the heater expands, and its density decreases, or you can say it becomes less dense. Its density increases. This causes, hence you can say, hence the hot less dense air rises up, rises up. And what will be your next point? You will say cooler, denser air. Oh, sorry. We have water in the beaker, right? Yeah. So you will change all these values to water, the water surrounding. The water surrounding the heater expands and its density decreases. Hence, the hot, less dense water rises up. Sorry for that, I didn't read the question. This is about water, so you will replace the wordings with water. Cooler, denser water sinks to the bottom. Cooler, denser water sinks to the bottom. Simple. Let's move ahead. The part of the boiler that holds the water is made from steel. Describe in terms of particle how thermal energy is transferred through steel. Okay. So what will we say? Vibration of molecules. Vibration of molecules causes the molecules to collide with each other, with each other. As the molecules collide, they they transfer energy, energy throughout the steel, throughout the steel. Simple. You will get a 3 on 3 in this. Okay, let's further move ahead. State and explain in terms of particle what happens to the density of the steel as the temperature increases. So, as the temperature increases, the volume of steel increases as it expands, and according to this formula, that is density is equals to mass over volume. If volume increases, density will decrease. So, you can say density decreases as volume increases as they are inversely proportional. Let's move on to the next question. A torch contains a filament lamp connected to a battery. The battery contains four 1.5 volt cells connected in series. The figure 11.1 shows the current potential difference graph for the filament lamp. Okay, so this is IV graph for the filament lamp. Okay. State what is meant by potential difference across the lamp. So potential difference is work done per unit charge, per unit charge in driving the charge, in driving the charge across the lamp, across the lamp. Let's move on to part 2. Figure 11.1 shows the current in the lamp is not proportional to potential difference. State how figure 11.1 shows this. The graph is a curve. The graph is a curve. Okay. Suggest why current is not proportional to potential difference. So you can say as voltage increases, what happens? Temperature increases. Can you see these parts are pretty repeating of a question that we have earlier done? As voltage increases, temperature increases. As temperature increases, your molecular vibrations increase. As your molecular vibrations increase, what will happen? Your resistance increase. Hence, voltage is not directly proportional to current. Let's further move ahead. Lamp is at normal brightness and there is a potential difference of 6 volts across the lamp. Use figure 11.1 to find the current in the lamp. Very, very easy. You will go here and at 6 volts you have this as your current. So let's extend this line. Yeah, this is your current at 6 volts. So let's see here. If we zoom in a bit, 1 2 3 4 5, yeah, so this is what 350 milliampere. Your current is 350 milliampere. Okay, so now if your current is 350 milliampere, voltage is 6. I think the next part would be energy. I think so. 350 milliampere is your answer. Calculate the charge that passes through the lamp in 2 hours. So you have to calculate the charge. Charge is equals to IT. Current is 350, 10 raised to the power of minus 3 into the time, that is 2 into 60 into 60. So let's calculate this. 350 into 10 raised to the power of minus 3. Why? Due to the milliampere thing. Multiplied by 2, multiplied by 60, multiplied by 60. This comes out to be 2520 is your charge. 2520 is your charge. 2520 coulombs is your charge. The battery in the torch is able to keep the lamp till 2 hours. Okay. Estimate the initial energy stored in the battery. Okay. As I told you, we might be asked to calculate the energy. Energy is equals to current voltage into time. What is the current? The current was 350 milliamperes. So 350 into 10 raised to the power of minus 3. What is the voltage? Voltage is 6. What is the time? 2 hours, 2 into 60 into 60. Let's calculate this. 2 into 3600 into 6 into 350 into 10 raised to the power of minus 3. This comes out to be 15120 joules. Explain why your value is only an estimate. Okay, our value is only an estimate because there will be heat losses through the wire. Simple, I guess it's 1 mark, so that's enough. Suggest and explain an advantage of using two cells in parallel rather than a single cell. The cell, the cell, the two cells in parallel last longer than a single cell in series. Why? Because the parallel cells have a greater energy. The parallel cells have greater energy. Simple. Let's further move ahead. An other torch contains a light emitting diode LED instead of a filament lamp. The battery in the torch uses four 1.5 volt cells, some in series, some in parallel. The potential difference across the LED is 3 volts. In the space below, draw a circuit to show how the four cells, a switch, and the LED are connected. First of all, to create 3 volts, how will your cells be connected? 1.5 and 1.5 will be connected in parallel like this. And then you will have two 1.5s again connected in parallel like this. This is 1.5, this is 1.5. This is 1.5, this is 1.5. The total voltage will become 3 volts. And let's say you have a switch like this and an LED like this. Figure 6.1 shows an electric circuit containing a filament lamp, a resistor, a 12 volts battery, and 5 meters. Okay, so you have a 12 volts battery, you have a resistor R, you have a filament lamp, and you have 5 meters. Okay, one second. The reading on ammeter 1 is 0.25 ampere. Okay, so this ammeter is reading 0.25 ampere. So if the current in series at one place is 0.25 ampere, the current at this will also be 0.25, and here also it will be 0.25, because the current in a series circuit remains same throughout. So let's see if we are asked about these readings. Yes, A2 and A3 we are asked about it, 0.25 and 0.25, because current in series remain constant. The reading on the voltmeter 1 is 3 volts. Okay, the reading here is 3 volts. Okay, you have to calculate the reading on voltmeter 2 as well. Okay, so the total voltage of the battery is what? 12. Let's say you have an initial pocket money of 12 rupees. You have spent 3 volts or 3 rupees on chocolates. What will be your remaining voltage or the remaining pocket money? 12 minus 3, that is 9 volts. So you can write 9 here. Simple. Let's further move ahead. Calculate the resistance of resistor R. You have to calculate the resistance of this resistor R. The voltage across this is 9. The current across this is 0.25 ampere. Can I calculate the resistance? Yes, V over I is equals to your resistance. 9 over 0.25. What will your answer be? 9 divided by 0.25. This gives you an answer of 36 ohms as your resistance. So let's write it here. 36 ohm is your resistance. The resistor obeys Ohm's law. State Ohm's law. Ohm's law basically means voltage or potential difference. You can write anything here. Voltage slash potential difference is directly proportional to what? Is directly proportional to current. is directly proportional to current, is directly proportional to current, given that given that temperature remains constant, remains constant. Okay. Figure 6.2 shows the current voltage graph for the filament lamp. Okay. The battery in figure 6.1 is replaced with a different battery which has a different electromotive force. The voltage across the lamp increases to 6 volts. Okay, so the voltage across the lamp now increases to 6 volts. So we have replaced this battery with another battery. Let's say that battery has a voltage of X volts, and this causes the voltage in this lamp to increase to 6 volts. Okay. This is what has happened up till now. Okay, so the examiner is asking us to use the data from graph to determine the EMF of the second battery. So basically we have to determine this X volts. We have to determine the EMF of the battery. Okay. So let's start step by step. So first of all, at a voltage of 6, what will be the current? At a voltage of 6, the current in the filament lamp is 0.35 ampere. Okay, the current in the lamp at 6 volt is 0.35 ampere. If the current in the lamp is 0.35 ampere, according to series circuits, the current in the resistor will also be 0.35 ampere. And you already know the resistance of the resistor. Can you calculate the voltage across this resistor? Yes, voltage is equals to IR. Current is 0.35. Your resistance is 36. Multiply it. 35 into 36. This comes out to be 12.6. Yes, 12.6 volts. So this resistor is getting 12.6 volts. This lamp is getting 6 volts. Add both of them to get the total voltage that you can write here. Although you can copy the above working as well here, but I'm just writing the final answer here. The lamp is receiving 6 volts, the resistor is receiving 12.6 volts. Add both of them up to get an answer of 18.6 volts. Simple. Let's move on to this question. A student connects a battery to two resistors. The circuit diagram is shown in figure 10.1. The potential difference across the 40 ohm resistor is 9.6 volts. Okay, so the potential difference across this is 9.6 volts. State what is meant by potential difference across a resistor. Very, very easy. Work done per unit charge, per unit charge. In moving a charge, in moving a charge across the resistor, across the resistor. Simple as that. Calculate the current in the 40 ohm resistor. You have the voltage, you have the resistance, you will apply V is equals to IR. Voltage is 9.6 divided by the resistance, that is 40. You will get your current. 9.6 divided by 40. This gives you an answer of 0.24 ampere is your current. Simple. Let's further move ahead. Calculate the electromotive force of the battery. You have to calculate the electromotive force EMF here. Very easy again. If this 40 ohm resistor is getting 0.24 ampere, this 10 ohm resistor will also get 0.24 ampere. The resistance is 10 ohm. Can you calculate the voltage across this resistor? Yeah. V is equals to IR. The current is 0.24. The resistance is 10. The voltage comes out to be 2.4. The voltage across this 10 ohm resistance is 2.4. The voltage across the 40 ohm resistor is 9.6. Add both of them up. This comes out to be 12 volts as your EMF. Your EMF comes out to be 12 volts. Okay. The student has three different voltmeters to measure the potential difference across the 40 ohm resistor. What was the voltage? Across the 40 ohm resistor, what was the voltage that we were having? Across the 40 ohm resistor, the voltage that we were having was 9.6 volts. Simple as that. 9.6 volts was the voltage across the 40 ohm resistor. Okay. So how will we measure this? How are we going to measure this? Very easy. There are three labeled voltmeters: 0 to 2 volts, 0 to 20 volts, 0 to 200 volts. Which will we use? We will use 0 to 20 volts voltmeter. We will utilize, state and explain. We will use which voltmeter? 0 till 20 volts. And what is the reasoning? Because the 0 to 2 volts is very small, has a very small scale, you can say that, has a very small scale, has a very small scale. And you can say, so you can say that because the 0 to 2 volts has a very small scale. And what is the problem with 0 to 200 volts? It has a very large scale. The 0 to 200 volts has a very large scale. Hence, the deflection will be very small. Hence, the deflection will be really negligible. Will be negligible. You can write that. Negligible is something that the examiners use again and again. Calculate the power dissipated in the 10 ohm resistor. You have to calculate the power dissipated in this 10 ohm resistor. The voltage across this is 2.4. Okay, the current across this is 0.24. So power is equals to IV. The current is 0.24. The voltage was 2.4, right? Yeah, 2.4. Multiply both of them, you will get your power. 0.24 into 2.4. This gives you a value of what? 0.7, 0.58. 0.58 volts is your power. The student has available two 10 ohms resistor with power rating of 1 upon 2p and 2p. Okay. Suggest why a resistor with a power rating of 1 upon 2p is not suitable for the circuit in figure 10.1, because it will get heat up and will eventually blow off. Will eventually blow off. Closing the circuit off, yeah, you can say disturbing the circuit. You can write that as well. Okay, let's read this question out. The student adds a resistor R in the circuit to make the circuit shown in figure 10.2. Okay. Complete the table in figure 10.3 to show what happens as resistor R is connected. You should state whether each quantity increase, decrease, or stays the same, and give a brief explanation of why any change occurs. Okay, calculations are not required. As you connect a resistor R in parallel, what will happen? The current in the 10 ohm resistance would increase. Why? Because the total resistance of the circuit decreases. Total resistance of the circuit decreases. Simple. Let's move on to the second thing. What will happen to the potential difference across the 10 ohm resistor? What will happen to the potential difference across the 10 ohm resistor? You will say that the potential difference increases. Potential difference increases. Why is that the case? Because current in the circuit increases. In the circuit increases. Simple. What happens to potential difference across the 40 ohm resistor? What will happen to the potential difference across this resistor? It will decrease. It will decrease. Why is that the case? Why is that the case? Because according to potential divider rule, potential divider rule, as voltage across 10 ohm resistor increase, as voltage across 10 ohm resistor increase, the voltage across 40 ohm resistor should decrease to keep the overall voltage constant. To keep the overall voltage of the battery same. To keep the overall voltage or EMF of the battery same. Obviously, you don't need to write all this story. You can write 1 to 2 lines from here and you will get the full marks. You can write till here. You can write according to potential divider rule, as voltage across 10 ohm increases, voltage across 40 ohm will decrease. You can finish your answer here. Simple. Measurements are made of the current in a metal wire and potential difference across it. Okay, so this is the current versus voltage graph. Figure 10.1 shows a graph of the current against the potential difference for the wire. Okay. State the relationship between current and potential difference for the metal wire. So you can say voltage or potential difference, since potential difference is mentioned in the question. Potential difference is directly proportional to current. Potential difference is what? Directly proportional to current. Directly proportional to current. Simple as that. Potential difference in a wire is directly proportional to current. State how the graph shows the temperature of the wire does not change in the experiment. How do we know that temperature of the wire does not change in the experiment? Because the graph is a straight line. Because graph, the graph is a straight line. What does a straight line graph tell us? A straight line. This means that resistance is constant, and hence if resistance is constant, temperature does not change. Temperature does not change. Simple logic, nothing complicated here. Let's further move ahead. An other wire of the same material has the same length as the original wire but has only half the cross sectional area. Okay, compare the resistance of the new wire and the original wire. Okay, an other wire of the same material has the same length as the original wire but only half the cross sectional area. So we know that resistance is inversely proportional to area. If you half the area, what will happen to the resistance? It will double. Compare the resistance of the new wire and the original wire. So we can say that the resistance doubles. Resistance doubles. Resistance of the new wire doubles. You can say that as well. Let me write it correctly. Resistance of the new wire doubles. Of the new wire doubles. Okay. On figure 10.1, draw the graph for the new wire. Okay, we have to now draw the graph for the new wire. If you notice here, the original wire has a resistance of what? The original wire has a resistance of what? 5 divided by the current, that is 0.4. This comes out to be 5 divided by 0.4. This comes out to be 12. Yeah, voltage is 5, current is 0.4. I guess I am doing it correctly. Yeah. The resistance comes out to be 12.5 ohms. For the resistance comes out to be 12.5 ohms for the original wire. Yep. Now, for the new wire, the resistance has doubled. So the resistance would be what? 25 ohm. Now, how can I get 25 ohm? If I keep my voltage same but I reduce the current, this should be my point. And then let's draw the graph here. Let's draw the graph like this. If you calculate the resistance of this wire, resistance is equals to voltage, that is 5 divided by current, that is 0.2. So 5 divided by 0.2, this comes out to be 25. Yes, the original wire has a resistance double of the initial wire. So yeah, this graph is correct. Let's further move ahead. 3 resistors are connected to a DC power supply as shown in figure 10.1. The electromotive force of the power supply is 6 volts. Okay. Calculate the total resistance of the circuit. We have to calculate the total resistance of the circuit. First of all, calculate the total resistance of this parallel combination. 1 over 20 plus 1 over 80 is equals to 1 over the total resistance. This comes out to be what? 1 over 20 plus 1 over 80 Reciprocate this answer. This gives you an answer of 16 ohm. So this entire parallel combination has a resistance of what? 16 ohms. So let's write it here. This is 24 ohms, and this parallel combination can be replaced with a 16 ohm resistor. Okay, let's further move ahead. You have to calculate the total resistance. Total resistance is 24 plus 16, that is 40 ohms. Okay. The current supplied by the power supply. How can you calculate the current supply? Very easy. Voltage is equals to IR. Voltage is what? 6, I guess. Yeah, voltage is 6 and total resistance is 40. Voltage is 6, total resistance is 40. Divide both of them. 6 divided by 40, your current comes out to be 0.15 ampere. 15 ampere. The potential difference across the 20 ohm resistor. Now you have to calculate the potential difference across the 20 ohm resistor. How will you do that? First of all, you know that the current is 0.15 ampere. Okay, and the resistance of this resistor is 24 ohm. So what will be the voltage eaten up by this resistor? V is equals to IR. Current is 0.15. Resistance is 24. Multiply both of them. Your voltage eaten up by this resistor comes out to be 3.6 volts. The total voltage is 6. What will be the voltage in this parallel combination? 6 minus 3.6, that is 2.4. So you can say that the voltage across the 20 ohm resistor will be 2.4. Here also you will have 2.4 volts since voltage in parallel remains same. So yeah, you can say that the voltage across the 20 ohm resistor is 2.4 volts. Okay. The DC power supply is a battery that contains a number of cells. Each cell has an electromotive force of 1.5 volts. What is meant by electromotive force of a cell? Work done per unit charge. Per unit charge. In moving a charge. In moving a charge across the complete circuit. Across the complete circuit. Simple as that. Let's further move ahead. In the space below, draw a diagram to show how four of these cells, okay, are connected to make a battery of 6 volts. Mark the positive terminal of each battery. Each cell has 1.5 volts. You have to make 6 volts. What will you do? You will connect all of them in series like this. This is the positive, 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 positive terminal. Also, you can write it here 1.5 volts, 1.5 volts, 1.5 volts, 1.5 volts, just to be safe. And connect them with a wire like this. Yep. This is your battery of 6 volts. Okay. In another arrangement, to produce a battery of EMF 6 volts, 8 cells, okay, 8 cells are now being used of EMF 1.5 volts, okay, are connected in this arrangement. Some cells are connected in series and some in parallel. In the space below, draw a diagram to show how 8 cells are connected to make the battery of 6 volts. Very easy. Positive, negative, positive, negative in a parallel combination like this. Okay. Then we have positive, negative again. Then a positive, negative again. They are connected in a parallel combination like this. Then we have the positive, negative again. Then the positive, negative again. They are connected in a parallel combination like this. Then we have the positive, negative again. Then the positive, negative again. They are connected in the parallel combination like this. Overall, this first connection has a voltage of 1.5 volts. This also has a 1.5 volts. This also has a 1.5 volts. This also has a 1.5 volts. Collectively, they give out 6 volts. Suggest one advantage of using a battery made from cells in parallel than a single cell. It lasts longer. Lasts longer. Simple. Okay, let's see this. Two lamps P and Q are connected to a battery of electromotive force 6 and an ammeter as shown in figure 6.1. Okay, lamp P has a resistance of 15 ohm. The ammeter reading is 0.65 ampere. Okay, so this is 6 volts. The ammeter reading is 0.65 ampere. The lamp P has a resistance of 15 ohms. Okay. Now let's further see what the examiner is asking. The current in lamp P. We have to calculate the current in lamp P. How will we do that? We know since lamp P is in a parallel combination with 6 volts, this battery will be receiving 6 volts. Resistance is 15 ohms. Can you calculate the current? V is equals to IR. 6 divided by resistance, that is 15, comes out to be your current. 6 divided by 1.5, this equals to what? 0.4 ampere is your current here. This is your current here. Okay. What will be the resistance of lamp Q? First of all, let's see the current in lamp Q, that is 0.25 ampere. The voltage in lamp Q is 6 volts. Can we calculate the resistance here? 6 divided by 0.25. This comes out to be what? 6 divided by 0.25. This is equals to 24 ohms as your resistance. The two lamps are now connected in series to the ammeter and the same battery. In the space below, draw the circuit diagram. Okay, two lamps P and Q, I guess, right? P and Q, they are connected in series, okay, to the ammeter and across the same battery. Okay, let's say this is your ammeter across the same battery. And do we have a switch? No, we don't have a switch. So let's just label it 6 volts. Let's place it like this. Okay. Explain why the ammeter reading is less than 0.65 ampere, because the resistance increased. Resistance increases as lamps are placed in series. Simple. Let's further move ahead. Okay, let's see this question next. Figure 7.1 shows two circuit components. For each of these components, state what causes an increase in resistance. For thermistor, what will cause an increase in resistance? Decrease in temperature. Decrease in temperature causes an increase in resistance. Okay. For LDR, what will cause an increase in resistance? Decrease in light intensity. Decrease in light intensity causes an increase in resistance. Okay. Let's further move ahead. Figure 7.2 shows a battery connected to a diode, an ammeter, and a resistor. Figure 7.3 shows the current voltage graph for the diode. Okay. The current in the resistor is 2 ampere and the potential difference across the resistor is 5.4 amperes. State what is meant by electromotive force of a battery. We have done this multiple times, but let's write it again. Electromotive force is what? Work done per unit charge, per unit charge in driving the charge through the complete circuit. In driving the charge through the complete circuit. Through the complete circuit. Perfect. Let's further move ahead. Explain why EMF of the battery must be greater than 5.4 volts. 5.4 volts is only consumed by this resistor. Why should the EMF be greater than 5.4 volts? Because some voltage is consumed by diode, is consumed by diode. So you will have to account for that as well. And some voltage is lost due to internal resistances, of the battery. Internal resistances of the battery. Let's zoom in a bit. Internal resistance of the battery. Simple. Let's move on to the next one. Calculate the electrical energy input to the resistor in 5 minutes. Okay, so we have to calculate energy. What is energy equals to? IVT. What is current? Current is 2. What is V? 5.4. So multiply it with time. Current is 2. V is 5.4. The time is 5 minutes. 5 into 60. This comes out to be what? 2 into 5.4 into 5 into 60. This comes out to be 3240. 3240 joules is your answer. The circuit is reconnected with the diode in the opposite direction as shown in figure 7.4. Explain what is observed. The ammeter reading drops to 0 as diode is reverse biased reverse biased, and offers a large resistance. Offers a large resistance. Let's move on to the next question. A 4.5 volt battery is connected in a circuit with an emitter, a light dependent resistor LDR, and a 800 ohms fixed resistor. Okay, so this is an 800 ohm fixed resistor. This is 4.5 volts. This is an LDR. Okay. The light dependent resistor LDR causes its resistance to be 9,000 ohms. Okay, so this is 9,000 ohms. The total resistance of the circuit, how will you calculate that? 1 upon 1800 plus 1 upon 9,000. 9,000 is equals to 1 upon RT. What will be your answer? 1 divided by 1800 plus 1 divided by 9,000. 1 divided by answer. This comes out to be 1500 as your total resistance. 1500 ohm as your total resistance. Your voltage is 4.5. What will be the reading on the ammeter? V is equals to IR. Voltage is 4.5 divided by the resistance 1500 ohms. 4.5 divided by answer. This gives you a value of 1 second. One. Okay, so can we? Yeah, this comes out to be 0.003 ampere as your answer. This is your answer for the current. Okay. Let's further move ahead. A very bright lamp is switched on, okay, and the intensity of the light incident on LDR increases, okay. So if the intensity of light on LDR increases, its resistance R will decrease. It will decrease from a value of 9,000 to a lower value, okay. Okay, so what will happen as the resistance of the LDR decreases, the current in the LDR will increase. What is the explanation? Current and resistance are inversely proportional. As resistance decreases, current increases. State and explain what happens to the current in the 1800 ohm resistor. It remains same or unchanged. Why is that the case? Why does the current in the 1800 ohm branch remain same or unchanged? Because the voltage across it, that is 4.5 volts, remain unchanged. The resistance remains unchanged. If both voltage and resistance remains unchanged, current remains unchanged. So you can write here voltage and slash resistance remains unchanged. Simple. Let's further move ahead to the next one. Okay, let's see this question. A student connects a battery with a thermistor X and a resistor Y in parallel as shown in figure 5.1. Okay. So this is a battery of EMF E. This is your thermistor X. This is your resistor Y. Okay. The electromotive force of the battery is E. The current in X is I. Okay. The resistance of Y is greater than the resistance of X. Okay. So the resistance of Y is greater than the resistance of X. Okay. Take two boxes to show the correct statement about the potential difference across Y and the other to show the current statement across Y. Okay. So the potential difference across Y is what? Same as the electromotive force E. Why? Because they are in parallel. This will also be E, this will also be E. The potential difference across both these branches will be E because they are connected in parallel. Okay. The current in Y is what? If you notice, the resistance of Y is greater than the resistance of X. And we know currents are inversely proportional. So the current in Y will be less than the current in X. So is there any options like that? It should be less than I. So yeah, it is less than I. That is the current in X. Okay, let's further move ahead. The student connects the thermistor in series with a resistor Y and a battery of EMF 6 volts as shown in figure 5.2. Okay. In the circuit at room temperature, the resistance of the thermistor is 600 ohm and the current is this. Calculate the power produced in the thermistor. We have to calculate the power produced in this thermistor. So power is equals to I square R. What is your I? Current in the thermistor. 0.002 square into the resistance of the thermistor, that is 600. So let's calculate it. 0.002 square into 600, This gives you a value of what? 2.4 into 10 is the power of minus 3 volts. Calculate the resistance of Y. We have to calculate the resistance of Y. Again, very, very easy. The current here is 0.002 ampere. Okay. Yeah. The current here is 0.002 ampere and the total EMF of the battery is 6 volts. Okay. Can you calculate the voltage taken up by this thermistor? Can you calculate the voltage taken up by this thermistor? Yes, you can do that. Voltage is equals to IR. The current is 0.002. What is the resistance here? 600. So 0.002 into 600, this comes out to be 1.2 volts. If 1.2 volts is eaten up by this thermistor, what is the remaining voltage that the Y resistor gets? The remaining voltage that resistor Y gets is 4.8 volts. The current is 0.02 amperes. Can you calculate the resistance? Yes. Resistance is equals to voltage over current. Voltage is 4.8 divided by current 0.002. Let's do that. 4.8 divided by 0.002. This comes out to be 24 ohms as your resistance for this resistor Y. Okay. The thermistor is cooled. Explain why this causes the potential difference across Y to decrease. Okay. The thermistor is cooled. Okay. This thermistor is cooled. If the thermistor cools, the resistance of X increases. And in series, we have studied voltage is directly proportional to resistance. If the resistance of X increases, the voltage across X will decrease. And according to the potential divider rule, as the voltage across X increases, the voltage across Y should decrease to keep the overall EMF constant. So, this is a lot of things to write here. Let's start one by one. Maybe I can write it in symbols and you can do the long form yourself. So basically, as temperature decreases, what happens? Resistance of X increases. As resistance of X increases, what happens? The voltage across X increases. Secondly, according to potential divider rule, potential divider rule, as Vx increases, what will happen? Voltage across Y decreases. And as voltage across Y decreases, according to potential divider rule, as Vx increases, Vy must decrease to keep overall EMF as constant. Simple. Let's further move ahead. Figure 3.1 shows a circuit containing 3 resistors, a 12 volt power supply, and an ammeter. Calculate the current in the 400 ohm resistor. Very easy. First of all, calculate the total resistance. The total resistance is 400 plus 200 plus 100, that is 700 ohms. The voltage is 12 volts. Can you calculate the current? V is equals to IR. Voltage is 12, resistance is 700. Your current comes out to be what? 12 divided by 700. This gives you a value of 0.017 ampere. Simple. Calculate the power produced in the 400 ohm resistor. You have to calculate the power produced in the 400 ohm resistor. Power is equals to I square R. I is 0.017 square. What is your resistance of 400? 400. So you can calculate the power here, square this value multiplied by 400. This gives you an answer of 0.118 volts according to three significant figures. Let's further move ahead. A student uses all of the components shown in figure 3.1 in another circuit. She connects them so that there is the largest possible current in each resistor. Whenever there is largest possible current, what is happening? Resistance is smallest. Resistance is smallest. And when is the resistance smallest? When all the resistors are connected in parallel. So at least by now I know 400, 200 and 100 amperes will be connected in parallel like this. 400, 200 and 100 will be connected in parallel like this. 400, 200 and 100. 400, 200 and 100 will be connected in parallel like this. Okay. The student connects the ammeter into the circuit to measure the current in this resistor. The current in one of the resistor is larger than the current in the other two resistors. Okay. Which resistor will have the largest current? 100 ohm, because it has the least resistance. So the student has placed an ammeter here. Okay. Draw the circuit diagram of the arrangement. Label each resistor. We have done that with the values of its resistance. Yeah, we have done that. What else is left? A battery is left. Yeah, so let's apply a battery as well of 12 volts like this. Our job is done. Let's further move ahead. Let's see this question. LDR is used to sense the amount of light in a room. Figure 6.1 shows part of the circuit used. The LDR is not shown. Okay. Complete figure 6.1 by drawing the symbol for LDR between P and Q. Very easy. How will you draw an LDR? Somewhat like this. Light is emitting from this LDR. Explain how the voltmeter reading changes as the amount of light falling on the LDR increases. As amount of light falling on LDR increases, what will happen? Resistance of LDR increases. Amount of light falling on the LDR, okay, increases. If the light intensity increases, the resistance of LDR will decrease. As the resistance of LDR decreases, the voltage across LDR decreases. As the voltage across LDR decreases, what will be your second statement? You will say, according to potential divider rule, according to potential divider rule, potential divider rule, what increases? The voltmeter reading increases to keep EMF of the battery constant, to keep EMF of the battery constant. Simple. Let's further move ahead to point B or part B. The current in the 4 ohm resistor is 2.4 amperes. Show that the current in the 5 ohm resistor is 1.9 ampere. Okay, very, very easy. First of all, can we calculate the voltage across this 4 ohm resistor? Can we calculate the voltage across this 4 ohm resistor? Yeah, we can do that. Voltage is equals to IR. Current is 2.4. Resistance is 4. Can we calculate this answer? 2.4 into 4. This comes out to be 9.6 volts. The voltage across this resistor is 9.6 volts and the voltage remains same in parallel. So across this resistor as well, you will have 9.6 volts. The resistance is 5 ohms. Can you calculate the current? Yes, V is equals to IR. Voltage is 9.6 divided by the resistance, that is 5, comes out to be your current. 9.6 divided by 5, this gives you a value of 1.92 ampere. Calculate the potential difference between X and Y. Okay, you have to calculate the total potential difference between X and Y. So this was 1.92 ampere. This is 2.4 amperes. What will be the combined current here? 1.92 plus 2.4. This comes out to be 4.32 ampere. So the current in this resistor, this green resistor, is what? 4.32 ampere. The resistance is 6 ohms. Can you calculate the voltage here? V is equals to IR. 4.32 into 6. This gives you a value of 26, you can say. This is 26 volts. This is 9.6 volts. Add both of them. 26 plus 9.6. This gives you a value of 35.5. 35.5 volts is your answer. Perfect. Let's further move ahead. Figure 9.1 is a circuit diagram. Okay, you have 12 volts battery, two resistors. Explain what is meant by electromotive force. I guess we have done this a lot of time in this video, so you can copy from any timestamp. An 18 ohm resistor and a 30 ohm resistor are connected in series with a battery. They state the relationship between the current in the battery. Okay, current in the battery IB, the current in resistor I1 and the current in resistor I2. In a series circuit, you know all the current throughout the circuit remains same. So current in the battery will be equal to the current in 18 ohm resistance will be equal to the current in 30 ohm resistance. State an equation that relates the EMF of the battery, the potential difference across 18 ohm, and the potential difference across 30 ohm. So we have to state an equation which relates the EMF to voltage 1 and voltage 2. We know what? In series, the combined voltage is equals to the EMF. V1 plus V2 is equals to the EMF. Calculate the current in the battery. Very easy. 12 volts. The total resistance is 48. Calculate the current. V is equals to IR. Total is 12. The resistance is 48. What does your current come out to be? What does your current come out to be? Current comes out to be 12 divided by 48. This gives you an answer of 0.25 ampere. Simple as that. Calculate the potential difference across the 18 ohm resistor. You have to calculate the potential difference across this 18 ohm resistor. So the current is what? 0.25. And the resistance is 18. So 0.25 into 18. This gives you an answer of what? This gives you an answer of 4.5 volts. Simple. Let's move ahead. Okay, now once you have calculated the potential difference across the 18 ohm resistor, the examiner is asking you to calculate the power dissipated across the 18 ohm resistor. So how will you do that? Power is equals to IV. What was the current across the 18 ohm resistor? Did we calculate the current? Yes, 0.25. What is the voltage? 4.5. Multiply both of them. 0.25 into 4.5. Your power comes out to be what? 0.25. This comes out to be 1.13 volts. The resistors obey Ohm's law. Okay. State Ohm's law and describe one limitation of this law. So what is Ohm's law? Ohm's law basically state voltage is directly proportional to current. And what is the limitation? Temperature remains constant. I guess we have done this before as well. Temperature remains constant. Okay, let's move on to the next one. The resistors are made from the same material but have different cross-sectional areas and different lengths. State the relationship between resistance and length. Resistance is directly proportional to length. State the relationship between resistance and cross-sectional area. Resistance is inversely proportional to area. Simple. Okay, let's see this question. Figure 8.1 shows the circuit diagram of a temperature gauge. It contains an ammeter, a thermistor, and a fixed resistor and a battery. Okay. The current is measured at different temperatures and a graph of the results is shown in figure 8.2. Okay. State how the resistance of the thermistor changes with temperature and explain how figure 8.2 shows this change. Okay. So basically, how does the resistance of thermistor changes with temperature? As temperature increases, what happens? As temperature increases, what happens? The resistance decreases. This is the relationship between the thermistor. You might get 1 mark here. How does figure 8.2 shows this? So as you can see in figure 8.2, as temperature increases, current increases. That means as temperature increases, resistance decreases. So this is shown in the graph as well. Let's further move ahead. Resistance and current are used for the measurement of. Okay, this has been excluded from the syllabus, so you don't need to do this question. A temperature scale that a temperature scale involves the use of fixed point. State what is meant by ice point, melting point of ice. However, I think this is also excluded. Melting point of ice. The steam point, that is the boiling point of water. Boiling point of water. But this is very, very easy. But these also have been excluded. At 80 degrees centigrade, the potential difference across the thermistor is 3.6 volts. State what is meant by potential difference. We have already done this multiple times. Calculate the resistance of the thermistor when temperature is 80 degrees centigrade. Okay. So when the temperature is 80 degrees centigrade, here your current is this, that is 0.014 ampere. Okay. When the temperature is 80 degrees centigrade, your current is 0.014 ampere. Your voltage is 3.6. Can you calculate the resistance? Voltage divided by current. Voltage is 3.6 divided by current 0.014. So let's calculate this answer. 3.6 divided by 0.014. This comes out to be what? 257 ohms as your resistance. The electromotive force of the battery is 25 volts. Okay. Calculate the resistance of the resistor R. Okay, let's see what the examiner is trying to say. So this is 25 volts as far as I can see, isn't it? The resistance, the electromotive force is 25 volts. Calculate the resistance of resistor R. Okay. We have to calculate the resistance of this resistor. Okay. So first of all, out of this 25 volts, can you see 3.6 volts? Yes. Can you see 3.6 volts is getting eaten up by the thermistor? What is the remaining value? 25 minus 3.6. That this resistor gets 21.4 volts is what this resistor gets. What is the current in the circuit? The current in the circuit is 0.014 ampere. Can you calculate the resistance? Resistance is equal to voltage over current. Voltage is 21.4. The current is 0.014. Can we calculate the answer? Yeah, we can do that. 0.014. This comes out to be 1530 ohms as your resistance. This marks the end of the past papers for current and electricity. If you have any questions, you may ask.